Hi everybody, welcome to this course on Internet Technologies. I am Vardan and today we'll be studying about the TCP/IP model and the TCP/IP protocol suite. So let's begin by understanding what the TCP/IP suite actually is. TCP and IP stand for Transmission Control Protocol and Internet Protocol. But when we're talking about TCP/IP suite, it's not just two protocols, it's a whole family of protocols that work together to manage data communication across networks. And the entire internet works on this TCP/IP suite. And the TCP/IP suite is designed to work in a connectionless environment where data is broken into independent units called datagrams. Each of these packets can take different paths to reach their destination, and TCP/IP ensures that even in this flexible and decentralized setup, communication remains reliable and scalable. Next, let's see how the TCP/IP model maps to the more widely taught OSI model. The OSI model has 7 layers, from the physical at the bottom to the application layer at the top. It's a theoretical model developed for standardizing network functions, but the TCP model, however, is implementation driven and it only has 4 layers. In the TCP IP, the application layer combines the OSI's application, presentation, and session layers. The transport layer stays the same in both models. The network layer, which can also be called the internet layer in the TCP IP, is same as the network layer in OSI, and it's responsible for routing and addressing. And now this is very important that TCP IP merges the OSI's data link and physical layers, and it is merged into one layer. It is called the network access layer, which is also called data link layer for simplicity. Because in modern systems, devices like NIC cards, that is network interface cards, handle both of the functions that are of data link and physical layers. The NIC transmits raw signals on the wire, and it also handles MAC addressing, framing, and error checking. And this is why TCP IP simplifies those bottom layers, and because the hardware is already designed to perform both roles together, and it's a practical approach that makes the TCP IP model better suited for real world networking. Each layer in the TCP IP model has a set of protocols that carry out specific tasks essential to data communication. At the application layer, protocols like HTTP handle web page delivery, SMTP manages email, DNS resolves domain names to IP addresses, and FTP or TFTP handle file transfers. The transport layer is responsible for ensuring reliable or fast communication between devices. TCP guarantees ordered, reliable, fast data delivery, while UDP offers a faster connectionless service useful for real-time applications. And coming to the network or the internet layer, it is responsible for addressing and routing. IP, that is the Internet Protocol, assigns addresses and directs packets to their destination. ICMP helps with error reporting and diagnostics. ARP resolves IP addresses to hardware MAC addresses. Finally, the data link layer or the network access layer defines how data moves across physical networks. It includes Ethernets for wired LANs, Wi-Fi for wireless connections, and protocols like PPP for point-to-point serious links. When data moves through a network, it passes sequentially through the TCP/IP layers. The application layer generates the data, like a web page request or an email. The transport layer then breaks this data into smaller segments, adds port numbers to identify the sending and receiving applications, and manages reliability depending on whether it uses TCP or UDP. Next, the internet layer wraps this segment into a packet by adding IP addresses for the source and destination along with routing instructions. Then the network access layer frames this packet and physically transmits it through the network interface card. The NIC converts the data into electrical, optical, or radio signals to travel through the physical network medium. At the receiving end, the process works in reverse. Each layer strips off its corresponding header and processes the remaining data before passing it up to the next layer. One of the most important concepts in network communication is encapsulation. As data passes down from the application layer to the physical medium, each layer adds its own control information in the form of headers and sometimes trailers. Why is this necessary? Because each layer in the TCP/IP model performs a specific job. The transport layer, for example, needs port numbers to identify which application sent the data. The internet layer requires IP addresses for routing. The network access layer needs hardware addresses and framing details. So, to do this, each layer encapsulates the data it receives by adding a header containing the information it needs. For instance, imagine the TFTP protocol, that is the trivial file transfer protocol. Let's say it sends a 200 byte message. The application layer would add a 4 byte TFTP header. Then the transport layer adds an 8 byte UDP header. The internet layer adds a 20 byte IP header, and finally the data link layer adds a 14 byte Ethernet header and 4 byte trailer. So the total size of the data on the wire becomes 250 bytes. This encapsulation process happens at the sender's end, and at the receiver side each layer reads and removes its corresponding header. This is called decapsulation, until and unless the original message reaches the application. At the heart of the network layer is the Internet Protocol or IP. It's a connectionless protocol, meaning it doesn't set up a dedicated connection before sending data. Instead, it relies on best effort delivery. It makes a reasonable attempt to deliver each packet, but there's no guarantee it will succeed. The IP protocol assigns a logical address called an IP address to each device in a network. This address is critical for routing, deciding which part to a packet should take through multiple routers to reach its destination. However, IP itself doesn't ensure that the packets arrive in order or even that they arrive at all. That responsibility falls to higher layer protocols like TCP, and to support its function, IP closely works with other protocols like ICMP for error reporting, ARP for mapping IP addresses to physical MAC addresses, and IGMP for managing group communications in multicasting setups. Both IPv4 and IPv6 are in use today, with IPv6 gradually replacing IPv4 to handle the shortage of available IP addresses worldwide. Moving up to the transport layer, one of its key protocols is TCP, that is Transmission Control Protocol. Unlike IP, TCP is a connection oriented protocol, and before it sends any data, it establishes a virtual connection between the sender and receiver using a three-way handshake process. In the three-way handshake, the client sends a TCP segment with the SYN flag set to 1, indicating that a request to establish a connection. This segment also includes a randomly generated sequence number. The server responds with a TCP segment that has both the SYN and ACK flag set to 1. The ACK flag is set to acknowledge the client's sequence number, and the server also includes its own randomly generated sequence number. The client sends a final TCP segment with the ACK flag set to 1. This segment acknowledges that the server's sequence number uh, and completing the handshake and establishing a connection. This ensures both devices are ready to communicate. The TCP provides reliable data transfer by guaranteeing that all packets arrive at their destination in order and without errors. If a packet is lost or corrupted in this approach, TCP automatically retransmits it. It also uses acknowledgements to confirm receipt of data and employs flow control mechanisms to prevent overwhelming slower devices or networks by themselves. Because of its reliability and order preserving features, TCP is used by applications where the data integrity matters. Something like web browsing with HTTP or file transfers with FTP or sending emails via SMTP and remote sessions with Telnet or SSH. Alongside TCP, the transport layer also uses the user datagram protocol or UDP. And unlike TCP, UDP is a connectionless protocol. It sends data without establishing a connection and doesn't perform acknowledgements, sequencing, or retransmissions. So why use UDP? Because it's lightweight and fast. Without the extra overhead of connection management and error checking, UDP is ideal for applications where the speed is more important than reliability. For instance, in voice over IP or VoIP or video streaming, it's better to skip a few data packets than to delay the entire stream waiting for lost packets to be resent. And for example, more DNS queries use UDP because the data exchange is small and usually one way. TFTP also, it is a simple version of FTP. It relies on UDP for lightweight transfers. So while UDP sacrifices reliability for speed, it's the perfect choice for specific applications that can tolerate a few loss in packets. In TCP/IP networks, multiple types of addresses work together to ensure data reaches the right place. The IP address is a logical address. It's assigned to each device in a network and it's used to route data across different networks. An example would be 192.168.1.5, and the MAC address is a hardware address, and that it is hard coded into our device's NIC card, and it identifies the device, any device on any network. It identifies it uniquely within the local network. Lastly, a port number identifies a specific application or a specific service running on a device. For instance, HTTP uses port 80, SMTP uses port 25, and this is essential because a device might have multiple applications communicating over the network simultaneously. And together, these addresses allow data to travel from right source application to the right destination application across different devices and different networks. And now let's bring it all together and see how data moves from the application layer down through the stack. And when you run an application like browser, it sends data to the transport layer, which decides whether to use TCP for reliable delivery or UDP for connectionless and a faster communication service. The transport layer adds headers containing port number and control information. And next, the data moves to the internet layer where the IP protocol adds source and destination IP addresses and routing instructions. The network access layer takes over, encapsulating the packet with MAC addresses, error checking bits, and framing details. And this layer then passes the data to the network interface card, which physically transmits it over the cable, Wi-Fi, or any other medium. On the receiving end, this entire process reverses, with each layer stripping its header until the original message reaches the application. And with that, we've come to the end of this lecture. And in the next one, we'll get a look at the IP datagram and the concept of fragmentation. And thank you for learning with me, and I'll see you next time.